Welcome. At the end of this lesson, you'll be able to learn and use an informal definition of a limit, define right and left-hand limits, and estimate a limit numerically. So let's look at some limit notation. This would be limit notation right here. What does that all mean? Well, LIM means the limit. We have to take the limit of something, so the limit of f of x. This part here means as x approaches c is equal to L. So you should add that into your notes. Let's take a look at the diagram here. All right, so let's see if we can find the limit of our function as x approaches c. So I'm just going to write limit as x approaches c of f of x. I'm also going to write in, I'm going to write in f of c. All right, so let's find those two things. All right, so if we look from the left-hand side and we look from the right-hand side, so we're coming from both sides of c there, right? We see that our function is approaching this value L. Right? So as we're coming from the left and the right-hand side, our function is approaching L. How about the value of our function at c? Right? Well, the value of our function at c, well, that doesn't exist. Right? We have a hole in our function. So when we're looking at limits, it's important to understand that a limit is not about what happens at the number that x is approaching. Right? So in our example above there, we are not interested in f of c. That's not what we're interested in. We're looking at limits. Instead, it's about what happens near or close to that number. We're interested in f of x as x approaches c. Right? So we're looking at limits. We're not talking about the value of the function per se. We're talking about the value the function is approaching for some value of x. Now, sometimes they're the same thing. The value of the function for some value of x and the limit of the function for some value of x are exactly the same. But sometimes they're not. Right? In this case, they're not, right? Because the value of our function doesn't even exist at c, but the limit still exists. So a very informal definition of a limit is what is happening to y as x gets close to a certain number. It's the height a function intends to reach. Let's talk about heights of functions. So heights of functions are the value of y. So for instance, what's the height of f of x equals x squared if x equals 2? Well, here we can just plug that in, right? The value of f of x when x equals 2 is just going to be 2 squared or 4. So sometimes our functions reach the height they intend. In this case over here, right? If we think of the function f of x equals x squared, the function equals 4. It reaches 4, right, when x equals 2. It reaches the height it intends to reach. Some functions don't reach their intended heights, but they do approach their intended height. A limit exists when a function approaches its intended height, regardless of whether or not a function reaches its intended height. So long as the value approaches from the right side and from the left side are the same as we travel along the function, the limit exists. Right? So if you put your finger on the left-hand side of some point and the right-hand side of some point, and you just follow along the function, and your two fingers come together and they're pointing at the same point, then your limit is going to exist at that point. So let's take a look at this example. Right? So what value does the function appear to approach as x approaches 2? Right? Well, let's find out the value of the function at 2. So what's f of 2? Right? Well, f of 2 here is equal to 5. Right? We have a point when x is 2, the function is 5. How about the limit of our function as x approaches 2? Right? So if we're coming from the left-hand side, and we're coming from the right-hand side, right? Notice those two sides, as we're coming closer and closer to 2, are approaching the same value. They're approaching 3. Notice that the value of the function is not the same as the limit of the function as x approaches 2. Right? So the limit of f of x as x approaches 2 does not equal f of 2. This happens to be a discontinuous function. The limit still exists, even though the value of the function does not equal the limit of the function. Let's look at another example. Pretty similar picture here. Right? So what value does the function appear to approach as x approaches 2? Right? So again, f of 2. Right? Well, now there's just a hole there. So f of 2 does not exist. We have a hole when x is equal to 2. But how about the limit as x approaches 2? Well, if we look from the left-hand side and we look from the right-hand side, the limit as x approaches 2 of f of x is equal to 3. Right? So here, the value of the function doesn't exist, but the limit does. And so another important point, the existence or value of a limit as x approaches a of our function does not depend on the existence or value of the function. All right? So just because f of a is not defined does not mean the limit as x approaches a won't be defined. Right? It's not dependent on the value of the function. So a limit is what is happening to y as x gets close to a certain number. Here we have an informal definition. Let's explain it in a little more detail. We'll look at a formal definition in a later lesson, but let y equal f of x be a function. Suppose that a and l are numbers, such that whenever x is close to a, but not equal to a, f of x is close to l. As x gets closer and closer to a, f of x gets closer and closer to l. Suppose that f of x can be made as close as we want to l by making x close to but not equal to a. Then we say the limit of f of x as x approaches a is l, and we write it using the correct limit notation. Okay? So we're looking at what's happening to the function as x gets closer and closer to some value. And our function is going to get closer and closer to the limit as x gets closer to a, so long as that limit exists. And we're going to look at in this lesson at limits that exist and don't exist. In AP Calculus, we'll be approaching problems in 3 different ways. Analytically, using the equation. And so in a later lesson, we'll use algebraic techniques to find the limit. Numerically, using a table of values. And graphically, investigating the graph. And so in this lesson, we're going to focus on table of values. I've used some graphs to help illustrate what a limit is, but we're going to be focusing on using a table of values to find a limit. All right, so let's look at this example. So we're going to be estimating a limit numerically. All right, so if we look at the value of the function here, so we're looking at the limit of the function as x approaches 0. All right, so if we look from the left-hand side, right, so we're looking for values that are less than 0, and we look from the right-hand side, right, so values greater than 0. As we get closer and closer to 0, is the function approaching the same value from the left-hand side and the right-hand side. Right? Well, it looks like from the left-hand side, we're approaching 6. Right? So as we're looking here from the left-hand side, it looks like we're approaching 6. From the right-hand side, it looks like we're approaching 6. So that means the limit as x approaches 0 of our function, x divided by the square root of x plus 9 minus 3, is going to be equal to 6. Right? So our limit exists because the limit as x approaches 0 of our function from the left-hand side. Actually, I'm going to write it. I'll use a notation later because I'm going to explain the notation later. Right? So the limit, I'll use words. The limit of f of x from the left-hand side equals the limit of f of x from the right-hand side. Right, so we're approaching the same value from the left-hand side and the right-hand side. Therefore, a limit exists, right? And that limit is going to be equal to 6 because that's the value our function is approaching as x approaches 0. Let's look at, I think I have one more example for us to look at right now. Okay, so we'll look at the limit as x approaches 4. Our function here is x divided by x plus 1 minus 4/5, and then all divided by x minus 4. All right, so let's look at some values, selected values of the function that are close to but not equal to 4. What happens if we plug in 4? Right, we're going to make our denominator equal to 0. Right, so we're undefined here. Right, so f of 4 does not exist, but does the limit exist? Right, so let's look from the left-hand side. Right? So we're looking at values of our function as for values of x that are a little less than 4, and we're looking at the values of our function for x values that are a little bit more than 4. Right? Are we coming from the left-hand side and the right-hand side? Are we approaching the same value? Right? Well, it looks like that we're approaching the same value from the left-hand side and the right-hand side. It looks like the limit as x approaches 4 of x of all that is equal to 0.04. Right? It looks like that's what we're approaching from both sides. Right? So here we've had some table of values to look at. In the next part of the lesson, we're going to do as a whole group lesson, and we're going to look at using the calculator to create our table of values and how we can use the calculator efficiently to be able to find a limit numerically. Bye for now, and see you in the next podcast.